Hello friends, this video on hydrocarbons part 5 is brought to you by examfear.com. No more fear from exam. Understand how to prepare alkanes. So there are various ways to prepare alkanes. One is from unsaturated hydrocarbon you are saturated, you add hydrogen and you get alkanes. You can get the alkanes from alkyl halides. You can get the alkanes from carboxylic acids. From carboxylic acid, you can do soda lime decarboxylation or electrolysis decarbosylation. So, using these techniques, you can prepare alkanes. We'll discuss these in details. Let's study from the first one, that is from the unsaturated hydrocarbon. So, you have unsaturated hydrocarbon, for example, alkene, alkyne, and you want to add hydrogen to it. Please note it's a little tricky process because generally we talk about the reactions we have talked about in the past chapter was about electrophilic or nucleophilic substitution, additions, reaction, right? So here if you see it's an elimination reaction where we are removing the hydrogens from the, we are adding the hydrogen to the unsaturated hydrocarbon, and this is done in the presence of catalysts like platinum, palladium, nickels. Please note it has to be finely divided and surface areas would be 1. And this process is called hydrogenation, where you add hydrogen to alkenes and alkynes to form alkanes in the presence of these catalysts. Why hydrogenation? Because you are adding hydrogen to it. Little tricky process, we'll discuss this process. But before we discuss this process, let's understand some more attributes about this process. The first is exothermic process. It gives heat. It gives heat. But still, if you see, it gives heat, but still it needs some catalyst to happen, right? Even without catalyst, it can happen, but it will be very, very slow. Still, it is exothermic. I'll discuss why it is. That it is exothermic, that means it gives heat, it gives energy, but still it is slow, right? And if you see with this catalyst, platinum and palladium, at room temperature, you can have the reaction. But if you use nickel catalyst, you need little high temperature and pressure. So generally we prefer platinum or palladium catalyst for this. And it is a syn addition. We will talk about syn addition. Why? Because the hydrogen get added in the same site. If you talk about stereochemistry and all, this is a syn addition. So this is a typical reaction I have. I have a ethene here, and I'm adding hydrogen in the presence of this catalyst. I'm getting ethane. And as I told, this is exothermic process, but still it requires catalyst because this is the graph actually. This is my, let's suppose, ethene, and you get ethane, right? Lower energy, right? Correct. This is my CH3, and let's suppose DS3. This is my CH2 double bond CH2. But if you see, you need some energy, right? For conversion, there is the threshold energy. So that's why even if this whole process is exothermic, because this much amount of heat is liberated, right? Because this is a change in energy. This is a higher energy, it is more stable, right? If you see, the ethane is more stable than ethene. So ethane finally you convert it to ethene, you got some energy. Correct? That's why it's exothermic. But still, there is a threshold required for the conversion, and that's why you need some catalyst here, or you need high pressure and high temperature, and it's very slow. Correct? The graph clearly shows why you need a catalyst or you need high pressure and temperature. Why it is slow, right? Because there's a threshold energy required for the conversion. Even though it is exothermic, for example, when you burn wood, right, it's exothermic, but it takes very fast. It happens very fast. There, this barrier is not there, but in this case, this is a barrier, and thus, from converting to ethene to ethane, you need some catalyst. And this is a typical reaction that happens. So here you see two hydrogens added in both sides. If you see the reaction mechanism, we'll discuss in the next slide. So you have hydrogen, and the hydrogen bond breaks, and then if you see this double bond also is weakened, and then one of the hydrogen is attached to this carbon. Suppose this carbon hydrogen is attached, and then the other hydrogen is attached to the other carbon. So in this case, in this way, you add hydrogen to this unsaturated compound. The other examples can be this guy. You have butane here, sorry, propine here. So in the propine, you are adding this hydrogen and you are getting this guy. So here you see you are adding two hydrogen because there are two double bonds that get broken. In fact, the triple bond that is broken. And if you see this, here also if you see, this is my propene, you add hydrogen this becomes propane. So let's discuss the reaction mechanism of the syn addition. So as I told, this is how it happens. The metal absorbs hydrogen gas, this is my metal, this absorbs hydrogen gas on the surface, and the strong hydrogen H sigma bond is broken and they're replaced with two weak metal hydrogen bond. So let me show you the animation with this. So the animation is my hydrogen, this strong sigma bond, and this is a hydrogen gas. So this hydrogen gas is absorbed by the metal and the bond is broken and you have this weak metal hydrogen bond. So this is a metal and this is a hydrogen. There is a bond between the metal and the hydrogen. If you see, they are two separate things now, right? There is no bond between these two hydrogen. This is the blue one is the metal, this blue is the metal, this is my hydrogen. So now there is a bond between this metal and the hydrogen, and there is a weak metal and hydrogen bond. Let me show you once again. There was a hydrogen gas with a sigma bond, strong bond, but the moment it came near to this metal, this bond is broken and you have now weak this metal and hydrogen bond. Now the pi bond of the alkenes, for example, this is my alkene here, right? They interact with the metal and the bond is weakened. So this is my alkene and this is my pi bond, correct? This is my pi bond. So this pi bond is also weakened when this alkene reacts with, or interacts with the metal. So if you see, this alkene comes near this metal and this bond is a little bit weakened, correct? Now what happens is the hydrogen is transferred, since this bond is weak now and this bond is also weak now, so this carbon wants more hydrogen, right? Because this bond is weak. So hydrogen is transferred from the catalyst to one of the carbon, the double bond. So if you see, one hydrogen will be transferred to this carbon, correct? And this bond is almost gone now, right? So if you see now, the second hydrogen will also be transferred from the catalyst surface to the alkane. If you see now, this hydrogen will also be transferred. So with this, what will happen is, this double bond which was there here, this will turn into a single bond. This will be a single bond now. If you see, what is this now? This is nothing but ethane. You started with ethene, this is ethane. Now the whole thing will go off from here, right? And the surface which is empty now will be used for the next hydrogenation of the next ethene molecule or any other unsaturated molecule, correct? So this will go off from here, right? You will take this from here and this space will be free now. Again, new hydrogen will come, the bond will break, then we will have weak metal hydrogen bond, and then one unsaturated hydrocarbon will come, hydrogen will be added, once satisfied it will go off, again a new unsaturated hydrocarbon will come, and this way the process will continue, correct? Hope you understand the mechanism where we have this hydrogenation. With this, let's take one numerical on this. So write all the structures of all the alkenes on which hydrogenation gives 2-methyl butane. So I have got 2-methyl butane, that means I have got something like this. Yeah, butane and 2 I have methyl. So I have to write the structure of all the alkenes. Alkenes, please note only alkenes, that means only double bond. So I can give a double bond, let's suppose at this position. So I'll get something like this. If I give it this position, it's all same. If I give it this position, this is all same. I can give it this position. Let me try with that. Correct. This is my second option. Correct. The third is I can give it this position. These two carbons. So it will be. So these are my 4 possible options. You can add hydrogen to it. These are my 4 possible structures of alkenes. if you, in all these, if you add hydrogen in the presence of any catalyst, it will give you this way. So as I told, there was a syn addition, right? And why it was syn addition? We have seen that both the hydrogens get added from the bottom. So if you see here, both the hydrogens get added from the bottom. And syn addition is something like this. If you have any hydrocarbon like this, right? And if you're adding from same side, it's called syn addition. So in this case, if you see, both the hydrogens is added from the same side, correct? So it is called syn addition. So let's have some proof to it.
Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.